Next up, we have Eswaraiah Chakali.
There we go. Whoa. Sorry, guys.
So you've used 10 minutes for green, and then 12 red as well. Nice.
Just 1 moment.
Yeah. Good evening, everybody. I'll be talking about the relation between filament and bipolar bubble versus magnetic field orientation towards one of the star forming region, RCW57A. So my name is Chakali Eswaraiah, and I am working with Shipping Lai at National Tsinghua University, Taiwan. So these are my collaborators. So I actually used SIRPOL H-band polarimetric data for this region. So the field of view of this polarimeter is actually 8 by 8 arc minute. So this recent space missions have unraveled that most of the molecular clouds are actually filamentary in nature. And these filamentary molecular clouds are actually associated with very nice bipolar bubble-like structures. So these are the two examples which are actually having a centrally elongated by filamentary molecular cloud, which is actually traced by 870 micron Atlas Gal dust continuum emission. And you can see in the background Spitzer images, you can see bipolar bubble-like structures. So the general understanding is that the bipolar bubbles are actually forms according to 2D hydrodynamic simulations. These bubbles actually forms due to anisotropic expansion of ionizing fronts. So if you have any embedded H2 region in a filament, the ionizing fronts actually travels with supersonic velocity in the above and below the plane. But along the plane, it actually encounters subsonic flows than in the perpendicular direction. So if we have magnetic fields in these structures, in the filaments, magnetic fields also actually introduces an additional anisotropic pressure, and we'd like to study the influence of magnetic fields on the evolution, formation and evolution of this bipolar bubble RCW57A. We know that magnetic fields are ubiquitous all over the Milky Way galaxy. In the galactic plane, they're actually parallel. In the giant molecular clouds, they're actually important and actually elongated perpendicular to the magnetic fields, and in the low density part, they're actually parallel and helping in the flow of neutral hydrogen material onto the molecular clouds. And if you see in the even more smaller scales, magnetic fields are extremely important from the formation of the formation to fragmentation and collapse, and also in the channelizing the outflows. So if you have magnetic fields along the expansion of ionizing fronts, they actually ionizing flows will be accelerated than in the perpendicular direction. So one of the implications is that young H2 regions actually are found to elongated along the galactic plane. So this is my target, which is located at 2.5 kpc. You can see this is the background image is a color composite image made by using a Spitzer IRAC image, 2 mass K band image, and DSS R band image. And you can see that this filament is not clear in the mid-infrared wavelengths, and bipolar bubble is very clear in the R band image, even in the H alpha images. And in the center, the H2 region is actually embedded, and from which the larger scale bipolar bubble is actually emerged. And if you see the distribution of interstellar objects, they are actually distributed along the filament. And if you see in the both gas as well as the dust continuum emission, this filament is actually further fragmented into different clumps, and each clump is actually further fragmented into cores. And these plus marks are actually the major sources, and there are many IRS sources are actually embedded within the H2 region. So this is very nice targets to study the importance of magnetic fields. In order to probe the magnetic field orientation within the star forming region, we have to separate out the stars which are actually intrinsically polarized, and which are actually less polarized foreground stars. So we have used near-infrared color diagram, and also polarization and polarization angle versus H minus k color. So in this diagram, you can see that most of the stars which are actually interstellar objects are actually shows large amount of intrinsic polarization. So we to only get a cleaned sample, we just exclude the intrinsically polarized interstellar objects, and then by using these diagrams, we actually see that the foreground stars are actually clearly show a single component of magnetic field orientation around 65 degree, and the background stars show the magnetic field orientation between 0 to 180 degrees. That means the distribution, you can see that they're actually randomly oriented than in the foreground component. And one of the important result is that the degree of polarization actually increases in increasing trend with H minus k color. So that is actually in accordance with the dichroic extension. Furthermore, some of the stars, we don't know their spectral types or their interstellar object nature. And by using the polarization efficiency diagrams, we also further exclude some of the stars which are actually depolarized because of the multiple magnetic field components in the background of the star forming region. So we have used these cleaned background sources to infer the magnetic field orientation in the star forming region. So this is the magnetic field orientation towards this RCW57A. So these red vectors actually probe the clear hourglass shape morphology. Most of the vectors are actually elongated perpendicular to the filament, and then they are clearly follows the bipolar bubble. So this blue area is actually a 7 by 7 arcmate SIRPOL image, and the background red color image is actually CO total integrated intensity image. You can clearly see this the green image is actually a Spitzer IRAC image. Most of the molecular cloud material actually been evacuated both above and below the plane. And this, you can see in the other parts of the cloud, you can still see the molecular cloud glass. So in order to see, we are not sure whether these magnetic fields are actually configured into hourglass shape, or the expanding ionizing fronts are actually configured the magnetic fields into hourglass shape morphology. So in order to check whether the magnetic fields are dominating or the thermal pressure is dominating, we estimate the magnetic field pressure using both the dispersion in the polarization angles as well as the velocity dispersion in the gas using the CO data. Since this image is actually a CO integrated intensity image on which we actually plotted the polarization vectors, you can see that since the magnetic fields are not actually exhibiting single component, we just divide all the portion into various parts, and each and every portion actually we estimate the magnetic field strength using Chandrasekhar-Fermi relation, and also we estimated the magnetic field pressure and also thermal pressure and the turbulent pressure. So when we compare this magnetic field pressure with both thermal pressure and the turbulent pressure, magnetic pressure is dominating over thermal as well as the turbulent pressures. So this indicates that magnetic fields are important in this region, and then magnetic fields could be primordially initially perpendicular to the filament, and so based upon these parameters and these observational evidences, we actually come up with this schematic diagram. Is that initially the magnetic fields are actually in this configuration. The cloud is actually spherical in nature. So because of the ambigular diffusion, the cloud has been actually compressed along the B field lines, and then further because of the accumulation of more mass at the center, the star formation actually been triggered, and the B fields are actually configured into hourglass shape morphology. So since we have the magnetic fields in hourglass shape morphology, so these expanding ionizing fronts can easily follow the B field lines to configure into a bipolar bubble-like structure. Yeah, this kind of observations are actually been there towards actually similar magnetic field orientation has been actually traced towards Serpent's molecular cloud as well as NGC 2024. So this scale of these regions they have actually probed is actually less than 1 parsec. And this kind of magnetic field orientation is very important. So in these results, they actually found that molecular outflows are actually pretty follow the magnetic field lines. And then these B fields are actually oriented perpendicular to the filament. And then you can see clearly how glass-shaped magnetic field lines. So this is very important for the formation of clusters according to outflow-driven turbulence model by Lee and Nakamura collaborators. So in which actually the turbulent outflow energy and outflow momentum will be ejected into the cloud, and actually magnetic fields will actually drives the outflows energy to escape from the central region to the ambient medium, and the gravitational inflow will take place in the perpendicular direction. So the competition between both the accretion and outflows will actually important in regulation of in regulating the cluster formation. So this is my summary. B fields are actually found not only important in the formation of filament, but also important in the formation and evolution of bipolar filament, like our target. And this kind of results are important for the driving of cluster formation. And you can see that our B field structure is confined to the low density parts, but we didn't yet trace the magnetic field orientation along the filament. So according to the envelope mass versus bolometric luminosity, so each and every core actually hosting different different class 0, class 1 sources. And according to this diagram, the cores which are actually lying very nearer to the central part are actually going to form class 1 sources, and the cores which are far away from the central region actually forming class 0 sources according to this diagram. So further, the submillimeter polarimetry with ASTE and ALMA will be highly desirable to understand the magnetic fields at lower scales.
I would be a bit more careful in interpreting the polarization in terms of magnetic field in your case. When we are talking about high latitudes, as in some earlier talks, it's probably okay, because alignment is not being suppressed in low density media with a lot of radiation. But in your case, you must have careful modeling, which will take the understanding and theory of grain alignment. Then you can say whether this is real, or maybe it's just or only the outer shell that has aligned grains.
Yeah, that's true actually. So in this kind of observations, actually, dusk grain alignment will be more efficient. And yeah, hello, can you hear me now? Yeah, I think this kind of the star forming region which we probe is actually having lots of ionized material, and you have the outflows. So you have lots of injecting energy to align the dust grains in a more efficient way.
I would also mostly worry about radiation, as radiation talks are proven to be the most important compared to mechanical talks.
Yeah, I think that's true.
All right, let's thank our speaker one more time.